Now, the first case let's look at. Okay, so taking our limit, let's say case 1. This is going to be the scenario where p is going to be less than 1. Okay, and our second case will be what happens if p is larger than 1. So if p is less than 1, what you're going to notice, and what we are interested in, is what happens with this term. This is the only term that has t in it. Okay, and so we would like to know if p is less than 1, what happens to that limit. So if p is less than 1, then 1 minus p, the exponent of that term, is going to be positive. Okay, and so therefore, when we do the limit as t approaches infinity, even of just this one term, okay, remember we're just focusing on that t to the 1 minus p term. Well, even just this one term, if that exponent is positive, then as the base goes to infinity, this whole thing is still going to approach positive infinity, and so it's going to be a limit that does not exist. And if just that one portion of the limit does not exist, then the whole thing is going to not exist. So we have our integral from 1 to infinity, 1 over x to the power of p. We know it's the limit as t approaches infinity, 1 over 1 minus p times t to the p, or t to the 1 minus p minus 1. And what we have just shown is that this part right here, that part is going to go to positive infinity. It's going to be dne, and so the whole thing then is going to be dne, because the whole thing is going to approach positive infinity. And that means altogether our integral is divergent. Okay, so that's the first case. What happens if p is less than 1? We get that our integral diverges. Now let's take a look at case 2. Okay, so very much the same thing, except that with case 2, we are interested in looking at what happens if p is larger than 1. And here, if p is larger than 1, then let's look at that same term, 1 minus p. Okay, we want to look at the exponent of this portion. And so that 1 minus p now, if p is larger than 1, it is going to be negative. And actually, if 1 minus p is negative, that means that p minus 1 is going to be positive. Okay, now why we care about this, you'll see in a moment. Okay, let's go and actually look at our limit again. We have a limit as t approaches infinity, and for now we're still just going to focus on that term t to the power of 1 minus p. So we know this exponent right here is negative, and so really we want to know what happens as t goes to infinity. We could sort of rewrite this. This is going to be 1 over t to the p minus 1. And so this is why we consider this p minus 1 term. We know p minus 1 is actually positive, so we know that this exponent here is actually positive, which means that now as t approaches infinity, this denominator is going to increase without bound. We have that our whole limit here is going to just go to 0. Okay, now we don't really so much care that it goes to 0, but we definitely care that this limit exists, this limit converges. So if we put the whole thing now together with the integral from 1 to infinity 1 over x to the power of p, if p is larger than 1, and we do our limit, we now know this part here just approaches 0. And so the whole limit altogether is just going to approach negative 1 from here, divided by 1 minus p from here. And really, we know that this number exists because we've already ruled out the case where p is equal to 1. And so actually we don't so much care, again, what this value actually is. All that we care about is that it is some number, that it exists. Okay, so now in this scenario, if p is larger than 1, we get that our integral converges. Okay, so we have covered those two cases. What happens if p is larger than 1? What happens if p is less than 1? And now we're going to take a look at the one thing that we left out from before. We would like to look at here. What happens if p is equal to 1? Okay, everything we did before was assuming that p was not 1, but what happens if p is equal to 1? So now, case 3. What happens if p is equal to 1? So now we have to go all the way back to our integral. Okay, and actually we already know that it's going to be the limit as t approaches infinity. Integral 1 to t, 1 over x to the power of p. Okay, except that we know that p is equal to positive 1, so we know that our integral is actually just going to be 1 over x. Okay, so there's no need to leave in that value of p, and now we know antiderivative for 1 over x, that's going to be ln absolute value of x from 1 to t. And actually, we know that this is one of the examples we covered early on. You should already sort of know what's going to happen with this integral. Let's finish it anyways, though, because it's not actually a long integral. We get limit as t approaches infinity, ln of t minus ln of 1. And here we know ln of 1 is just going to be 0. And we also know that for ln of t, as t approaches infinity, this is going to approach ln of an ever-increasing value, and so it itself is going to be ever-increasing. It is going to be dne. So for this limit is going to be positive infinity. It's going to be dne, and so altogether we get that our integral is divergent. Okay, so now let's go back. Let's summarize everything. If p is equal to 1, we have divergence. If p is larger than 1, we have convergence. And if p is less than 1, we also have divergence. So putting it all together, our conclusion is going to be that the integral from 1 to infinity, 1 over x to the power of p, is going to converge or diverge depending on that value of p. We know that it is going to be convergent for large values of p because for large values of p that function decreases faster towards 0 as x increases. And we know that it is going to be divergent for small values of p. That's p values less than 1, but also it diverges if p is equal to 1. And so this is very much the result that we were looking at. When does our p integral converge? It converges if p is specifically larger than 1.